So it was observed this talk could be in the non-standard applications as well, since I'll talk about Bayesian. I'll talk about influenza forecasting as an application, but it's also a different kind of modeling, and so I guess it fits under uncertainty quantification. So I'm Jim Gattiker, and Dave Ostis is the person who's not here, who's done a lot of the work that I'll talk about, and we're both in the statistical sciences group at Los Alamos. When I was invited to this session when it was being formed, it was suggested that this paper would be very interesting to this meeting, so I hope it is. So this is the one I'm going to talk about, and Dave Ostis is the first author on this paper, and so the organizer, of course, isn't here, but hopefully it'll go well. So there's Dave. He's the main investigator for this work, really pulling together the methodology. And as we'll explain, there's applied modeling that's ongoing. So thanks, Dave. This paper is also came out recently, but it's a discussion paper in Bayesian analysis. I think the discussions are available online, and the response to that is going to be forthcoming soon. Because this is an uncertainty quantification session, I think I wanted to just say a few words about what uncertainty quantification means. I think we're not going to get an emulators talk, so a Gaussian process response surface methods talk in this session, which is a little different for an uncertainty quantification type session. So I'm in the statistics group, and what do we do in statistics at Los Alamos? We do a lot of working with data, and so we can do regression analysis that leads to reliability analysis and hypothesis testing, and all the kinds of things you do with data. And all those things, because we're statistician, it comes with quantified uncertainty. So the question that many statisticians wonder is, what is this uncertainty quantification thing that sounds a lot like what we think of as statistics? And that really is that we use domain models when we talk about uncertainty quantification. So one thread of uncertainty quantification that's statistical uncertainty quantification, I'll say, is to, again, use data for prediction and discovery, but incorporating domain models as well. Often, usually maybe, the domain models are computational simulations. And that's where we get into numerical weather prediction analysis, computational physics, all these sorts of large simulation type applications. And in the statistics way of looking at it, domain models are just part of the statistical analysis, but they're a different type of information from observations or prior information that you bring to the table when you're doing an analysis. But still, as a statistical model, it includes uncertainty and all the inferences that we might want to do, inferences about unknown parameter settings, or inferences about model inadequacy, or data uncertainty, or even forecasting or extrapolation. And that is I don't want to cause controversy here. I think people aren't married to these fields in the room. There's maybe another thread of uncertainty quantification that comes from numerical analysis. And that is a concept based in solution methods for ODE systems. So looking at that and extending that type of methodology to dealing with unknown parameters and links to data. But ultimately, the objective is the same. It's making inferences, including uncertainty. And to that degree, these two things look the same at the end of the day, even though they come to the table with different things. I think data assimilation kind of goes across both of these areas. There's some very statistical components to it, as well as some very numerical analysis and dealing with ODE systems components to it. So hopefully we'll find some areas of common ground in this work that I'll talk about. I'll lead into this a little bit and talk about one of the important things that came out of the statistical uncertainty quantification. And the key advances sort of snowballed in the early 2000s. And in statistics, this work was based on response surface methods, which had a long history before that of modeling, say, simulation output with a Gaussian process or other sort of response surface. And that was important. And the current work is very based on that work. The reference there is Kennedy-O'Hagan. That's often considered the touchstone or turning point for Bayesian calibration in statistics. Another thread that came in is that we could analyze complex Bayesian models with Markov chain Monte Carlo with the computation that was available at that time. But really what's key here is that was introduced that I'll be talking a lot more about or stressing in this discussion is using the statistical concept of discrepancy between model and data, and really introducing that allowed us to think about what is the status of observations and how is that different from the status of models and how is that different than the status of priors that you bring to the table. So discrepancy is a very important consideration when you're considering modeling. Again, very simple equation. You have observed data is equal to a system model plus some discrepancy, then because we're statisticians, plus an error term. The discrepancy is ultimately supposed to capture the potential shortfalls of the model. Of course, if you knew what those shortfalls were, you'd probably put them into the model. So there's obviously some uncertainty about what's going on with the discrepancy. It's important that the discrepancy be consistent with the domain being modeled. That means both in terms of it's doing the right sort of thing that you need the discrepancy to do, and it also does things that are consistent with, say, conservation properties that are very important to the application at hand. A couple things important to realize are discrepancy and parameter bias trades off. So to the degree that the discrepancy isn't orthogonal to the variability of the model, these things can trade off. So you can say, well, I could change this parameter a little bit and get a better fit, or I could add discrepancy and get a better fit. And for that reason, in my mind, it's important to think about those things as kind of two sides of the same coin rather than very distinct objects of inference, since they're really not identifiable in the normal case. And of course, if you're looking at discrepancy as a statistical quantity, it's very difficult to justify an extrapolation why a discrepancy would get you out of sample to data that you've never seen before. And that's important to think about the rest of those things. So that's an introduction to discrepancy, which I'll talk more about. The overview of the rest of the talk is about this flu surveillance application and using that as a case study, I suppose. So influenza surveillance, we'll look at the data and forecasting objectives. We'll talk more about how we treat model inadequacy and discrepancy. We'll look at this dynamic Bayesian model and then the forecasting results and conclusions. Flu surveillance, I guess the first thing that I'm going to talk about, influenza, flu surveillance, although we don't really know whether the data that we're looking at is influenza or not. In the US, at least, there's not the capability to talk about whether somebody's sick from influenza versus sick from something else that looks a lot like influenza. That is, there's a temperature, there's a sore throat and cough, no other known cause that would lead to that of some other type of disease or syndrome. And the Center for Disease Control and Prevention, the CDC, monitors these influenza-like illness. And many providers participate in the network that they're used for monitoring. And this is where the data comes from that we're going to look at. So really, we're not trying to predict influenza. We're trying to predict this quantity ILI, which is a proxy for influenza. And of course, just to have a look at what the data looks like. This ILI data is released weekly by the CDC. It has both predictable and unpredictable features, meaning, well, the flu season starts low normally. We're not going to show things like the H1N1 outbreak, which was a very off-cycle outbreak and very unique. It ends low, and it has a peak in the middle. There's two different kinds of peaks, sort of you could think of it as the before the winter holidays peak and the after the winter holidays peak, and there's two different kinds of seasons to do that, qualitatively two different types of seasons. So it has those unpredictable features. It's unpredictable about what the peak intensity, where the peak location will be, and those are the things that we're interested in inferring. The CDC for several years has been running a competition, flu forecasting challenge, to probabilistically forecast these things, the peak intensity, the peak timing, onset, the short-term forecast 1 to 4 weeks ahead throughout the flu season. And the primary interest, of course, is forecast accuracy. The CDC now actually considers the entries in this flu competition as sort of advisors for how they deliver their advice. So this agency is the one that tells hospitals when they should be stocking up on the products that they need to treat influenza, when the peak might be, whether it's going to be a bad season or not, those sorts of things. So it's a very operational sort of forecasting thing. And I can say at this point that, again, the primary interest is forecast accuracy here for this work. So we're not thinking about inferring parameters or what the parameter accuracy is. We're not thinking about, are we getting the state space right? We're thinking about, are we getting the forecast pragmatically right as we look through a season? And we've participated, and when I say we, again, Dave is participating in these challenges in an ongoing way, and turns out to be a very competitive model in that area. So we want to get the peak timing and intensity, this look ahead in 1 to 4 week ahead, where that might be. And yeah, and do that forecast with a sensible uncertainty. So we'll base this on this mechanistic model, which probably everybody has heard about, the SIR, susceptible, infectious, recovered model. And we can talk about more complex models, but this is already a pretty complex model for this stuff. And there's no reason to think that fitting a more complex model no reason to think. There's evidence that fitting a more complex model doesn't lead necessarily to better forecasts, just because the model's not completely identifiable as it is. And again, we're interested in forecasting, not talking about how do we adjust parameters to get a more accurate model. So the model assumptions are unrealistic, of course. There's a closed population, there's homogeneous mixing, time invariant disease transmission. So these, of course, lead to inaccuracies in the model, which is where the discrepancy comes in. I'm not going to talk much about the parameters. It's also there's not enough information to identify this model, so you have to do things like set the susceptible population to a value going in that's unknown in reality. But it doesn't matter because we're not interested in that point. We're interested in the forecasting. So if you look at the model inadequacy, there's a few flu seasons compared to the best fitting SIR model when you adjust the parameters to find the best fit. When you do that across all the 4 flu seasons on record, you can see that there's a systematic deviation between the influenza-like illness and the best version of the SIR model results. The red and blue is, we don't know where these biases are. You can always speculate on these things. Is it because reporting is different before the holidays versus after the holidays? Is it because of the behavior change over the holidays? But there's always a little tick up to a red a peak and a little tick down after the holidays. The SIR model can't fit the tails correctly, so it's not adequate for the purpose. It's not clear that finding a different mechanistic model or process model would necessarily be a better thing to do. So instead, we're going to look at discrepancy structures. So ILI exhibits these commonalities across the flu season, and we can get the general shape of it, but discrepancy is definitely evident. And we're going to develop a statistical model that leverages all this information across flu seasons and gives us a good forecast, trying to strike a balance between this model structure and model flexibility with empirical models and the discrepancy. So this is where we get into Bayesian hierarchical modeling and trying to decompose the process into, so when we want to model the data, the process, and the discrepancy simultaneously, you can decompose the probability like that and treat each one of those separately. So the data is the ILI data. The process is motivated by the SIR model, so that one. And then the discrepancy is going to be, we'll talk more about that, a flexible function, capturing those differences. Is there anything new to say on this that I haven't already touched on? The SIR model is the proportion of the population affected. It's a very simple ODE model, but nonetheless is still a computational model technically because it's not solvable in analytic form. And we have these initial conditions and parameter values that we have to determine. How do we treat this value as a probabilistic quantity? The idea is that these parameters have to be uncertain, and so we use an empirical based sort of approach to look at the historical seasons, find the best fitting model, look at those parameter values, approximate that by a multivariate normal in each parameter value, truncated to make sure they're sensible and that it operates in the mode that looks like a flu season. And so we have that uncertainty then. And so now we have a process model augmented with uncertain parameters that models the flu seasons as best as that process model can. So when we look at the residual from that model, we can start talking about what that discrepancy might mean. The discrepancy here represented by psi will look at 2 components. And so the upper plot shows all those discrepancy profiles with one of them called out that we'll focus on. The first component is a mean of, it's statistical, but you can think of it as the component, the part of that process discrepancy that explains all seasons discrepancy from the SIR model as best as possible. But of course, that doesn't explain the season-by-season variation. Then the delta component is intended to explain the uncertainty in the season-by-season variation that we see unaccounted for by the mu part of the model. the way we model this in this case, and this, again, we're interested in this specific forecasting application, so we're motivating this from a number of choices that were investigated by its performance and prediction. The reverse random walk process looks at the end of the flu season. I didn't mention before, but if you looked at what an SIR model does, it's almost uniformly two variable at the end of the season, whereas we have one data point that we are pretty sure about, that flu seasons end in, say, May, and they go to a very small amount of endemic flu in the population. And so starting from that point where we know something about that, and because we're interested in forecasting the end of the season and not talking about the beginning of the season after we already have data, this process that depends on that and has a sort of a negative time dependence, as described there with mu t and delta t, where the j now is on delta indexes of the different flu seasons, turns out to be a good way to model that. This has some roots in models for financial forecasting as well, and has been investigated in that framework. So borrowing from there, we can get this reverse random walk process that has the features as shown. We're modeling the model on a logit scale, because that allows us to not worry about going below 0 and expanding the domain out appropriately. The total model then, the data model, now we're up to data given the process and discrepancy models, looks like this. So we have the I, the infectious population from the SIR model, it's that component, and the logit of that, so expanded out so we don't have to worry about going below 0, plus this mu component, which says between the total season uncertainty as best as can be explained, plus the delta, which is the individual season discrepancy as best as can be explained, is the logit of pi, which is our estimate of, our best estimate of the mean estimate of our future forecast. The actual future forecast value is a beta distribution based on that in that logit scale. There's a lambda parameter running around which says how much uncertainty should be there that's tuned. Lambda is a tuned parameter, looking at all the data that we have so far. And again, you can refer back to the paper for all these specific values. Other things about the parameters in the discrepancies, the parameters in the rest of the model that we've gone over, are components that can be sampled with MCMC when this whole thing comes together as one resolved model that has all the dependencies. Given all the historical data and the data in the flu season so far, we can fit this model as well with a standard MCMC type tool like JUMP or other. And finally, get to posterior distributions. Columns in this one are going through a historic flu season, as if we haven't seen all the data. So it starts at, the first one is week, I guess, 5 of the flu season, then week 15, then week 25, and what those predictions look like. So it starts out very uncertain, as you'd expect. As you lead into a flu season, that trajectory doesn't tell you too much about what's going on. But as you go through it, you pick up more information and can make sensible forecasts about what's going on. This shows on the top level what we think the future data, the future flu season is. So that's the main predictive product given the data so far. But we can break out the components. The process model is that SIR model. So that looks very smooth, as you'd expect, because it can only manage to do some variations. This shows the feature of the process model that I mentioned, that at the end of the flu season it's far too uncertain. And you can see that the discrepancy model then is talking about at the end of that flu season it's doing something commensurate to offset that uncertainty there. Using JAG's fitting tool. Talking about the forecasting challenge itself, so this is very operational. You put in your guess as the season goes on, and you're judged in retrospect by the forecasts you put on record. They're not necessarily the perfect scoring rules, but they do try to give some allowance for peak timing and probability. So the notion is at the end of the season, you have found out when that peak is, and you can judge the accuracy of a forecast by saying how much of the future forecast probability for, in this case, we're looking at peak intensity and location, was within plus or minus 1 week of the known peak, and get some credit for being able to identify it that way. part of the exciting part of the paper is that this does very well in the CDC challenge. When you look at all these different, so the criteria here are the overall log score, then there's the 4-week, 3-week, 2-week, and 1-week prediction. They all have scoring methods that are along the lines of what I talked about. There's the onset, the peak intensity, the peak timing. So those all have particular ways to express them. And so this model is doing very well. So there's 14 raw models. I think the thing that we find very exciting is that this is a different kind of approach that's not along the lines of the traditional models that the CDC would have entered or use in their flu forecasting. And so when we look at 30 models, in 2016, 2017, and more. As is popular these days, you wouldn't expect to just use one model, but you're going to choose your best model and try to blend them in some way to give even better results. And so having a model that has somewhat non-correlated errors and forecast qualities with the existing models is a contribution that leads to even better leveraged models. So sort of a new category of instrument that we use to combine into the portfolio. Another, just to defend the value of the discrepancy, which again, the purpose of the talk largely is to convince you that this discrepancy component is something that's important to talk about. In the 16-17 challenge, the no discrepancy model versus the discrepancy model was entered and has these different scores. 0 would be the top level of score, so it's uniformly better and definitely adds to the forecast accuracy. So summary of that part, of the application part. The SIR disease transition model can't capture all features, nor could any model of disease transmission because it's just not identifiable given the data that we have. Discrepancy accounts for these systematic deviations between the disease transmission model and ILI data. And by exploiting a hierarchical model across the whole domain that reconciles all these different components, we can get an optimal combination of those things which improves the ILI forecasts. And discrepancy modeling should be considered, of course, in modeling and forecasting. If we're curious about what's going on this year, a couple different directions. This year it's not just across the US forecasting as a general population, but these are different regional forecasts. So it's showing the historic regional profiles and what our forecast this year looks like. So that's a new direction since the paper that we're discussing was put together, and so that's in process this year. Another thing that's interesting is to look at proxy data sources. For example, Wikipedia data is another direction that has been looked at here about whether those data sources can be leveraged. That's true with mixed results. The overall forecast looks like this year. This is the national level forecast. So you can see that possibly we've seen a peak, but we're also moving. The mean forecast looks like we're looking at a 2-peak sort of a year, which is unusual, or it could accelerate into a much bigger peak. Down here in the bottom corner, predict.cdc.gov is where these flu forecasting sites are. So you can always follow along with their flu site database and look at this contest and consider entering your own model if you're interested in doing that. So this is the question slide. I'll do one more quick questions slide, which is just to talk about Los Alamos a little bit. We're always recruiting statisticians, and there's lots of summer schools and things like that for students. So if you're looking at the US, consider looking at the national labs. There's machine learning summer schools, high performance computing summer schools, and of course we have lots of opportunities in statistics as well. So I'll take questions or discussion.
Thank you very much. Okay.